Time to look at some CNN modifications. This time we're going to focus on modifications that you can make to your machine learning models that are actually unique to convolutional neural networks. Okay, let us start with a grid of pixels. Consider a grid of the following 9 pixels. Look at that. A little bit uninteresting. Just think of it as a grid of 9 numbers where each pixel, the larger, the more brightness. Now imagine a 2x2 filter that performs convolutions. So for instance, if you look at the blue square, it's hovering over 4 numbers, it's going to perform a convolution on those 4 numbers. How many times will the upper left one be part of a convolution? So the idea, right, is that the filter is going to go across the entire grid. Okay, well, to begin with, there's the number 1. It's being used in the first filter. Not being used in the second filter. It's not being used in the third filter. And no surprises here, it's not being used in the fourth filter. So in fact, the upper left one is only used 1 time. Now consider how many times will the middle 3 be part of a convolution. So starting back at the beginning, there the middle 3 is a part of the first convolution. There it's part of the second convolution. There it's part of the third convolution. And there it is part of the fourth convolution. So the middle 3 is used 4 times. And you can also easily confirm that, like, if you look at, say, the one on the right side, that one is in fact used twice. Okay, so there's potentially an issue here. And padding is potentially the solution. So you can use padding equals same as a parameter for the convolutional neural networks. And that's what it does. It actually creates a border, and by doing that, the idea of padding equals same is that each pixel will be used in the same number of convolutions. Okay? So in this case, it would be 4 times because we have a 2x2 grid. If we count the ones one more time, that particular upper left one, you can see it's part of the first convolution, part of the second convolution, part of the third convolution, and part of the fourth convolution. Okay? Padding equals same is a common parameter that is changed. Okay? So what's the padding advantage? Well, when using padding equals same, all pixels have equal influence. Relatively speaking, I mean, it's different, I think, when you have a number in the middle and it's next to other pixels, and then the one in the corner when you put an arbitrary border up there. Okay, so they're used the same number of times. Otherwise, pixels at the center are worth more than the edges. Why? Well, they show up in more convolutions. There are additional padding options. I'm not going to go over them now. Just note that padding equals same is kind of like a standard alternative. And of course, you can always look up the additional options to see the slight differences. Okay, but I can tell you that the main norms that you see are padding equals same and then no change to padding. This is something called padding equals valid that I've seen. So we could look into that later. But let's look at something else right now called strides. Okay, so another modification is called strides. Instead of moving 1 unit to the right, a stride of 2 will move 2 units to the right. Now we're talking about filters here again. So if we consider our padded grid of pixels, and we start with our 2x2 filter, if we implement stride equals 2, then you can see it moves over 2 units to the right instead of 1. So what's the stride advantage? Well, a stride greater than 1 greatly reduces the number of parameters. A stride greater than 1 also limits the influence of individual pixels because they're used less times. Okay, there's something similar but different called the dilation rate. So what is this? Dilation rate allows for the pixels within each filter to spread out. See, a stride moves the filter a greater distance, whereas dilation moves the filter, the individual pixels, out more. So a dilation rate of 2 will include every other pixel in the convolution. So again, if we have our padded grid of pixels, there's a dilation rate of 2. you can see it's still a 2x2 filter, but instead of using the 4 pixels closer together, it uses 4 that are spread apart. And with a stride of 1, that's what would happen. And you have to have a stride of 1, strangely, with a dilation rate greater than 1. I'm sure it could be hard-coded otherwise, but those defaults are currently not permitted in Keras. So what are some dilation rate facts? Dilation rate greater than 1 greatly reduces number of parameters, right? Am I meaning pixels there? Dilation rate greater than 1 and strides greater than 1 are incompatible, as mentioned. You know, it does reduce the number of parameters because the number of parameters is in fact like the number of weights, and you're not like, if you look at it across a whole image, you're just not going to have as many convolutions, okay, because you're spreading across greater distances. Okay, now let's look at a final concept called average pooling. We had max pooling before, but you can also use average pooling. I think the name here is kind of self-explanatory. Instead of taking the max pixel in a group, average pooling takes the average pixel in a group. So if we look again at our grid of padded pixels, we could consider the following filter with the following 4 numbers in it. Well, max pooling will it'll reduce that group of 4 down to 4. And average pooling will reduce down to the average of those 4 numbers, which is 2.5. So what about average pooling versus max pooling? Well, max pooling focuses on brighter parts of the image, right? Because it gives you the max. And average pooling smooths out the features. Like, you know, if you're looking for more subtle features, you should try average pooling, okay? And again, the name of the game for us is going to be experimentation. These are things that we can try and see the results. Sometimes results go with your intuitions and sometimes they don't. All right, I'm excited to try it in Colab Notebooks. Let's see how we do.